Good afternoon slash morning slash evening slash whenever time it is local to you when you're watching this. In class I said I was going to put up a screencast about how we get these equations, talking about series and parallel circuits. And so here we go. This is going to be our little discussion about how we simplify circuits and where on earth these equations come from. It's going to talk a little bit about these equations, and it's going to talk a little bit about Kirchhoff's laws, which govern kind of how we do circuit analysis. So let's start with the series case. Not the serious case, that's something totally different. So if I have a series circuit, I guess I was doing blue. This means that I have resistors in sequence one after the other. So I have some R1, some R2, and I have some battery supplying a voltage V0. And I claim that I can replace this by an equivalent circuit. And this equivalent circuit still has my battery V0, but it has instead this new equivalent resistor, and that is what REQ is standing for. And so what I'm saying is basically that I'm replacing the contents of this black box with the contents of this one, and that I can't tell the difference. I wouldn't be able to say if it were the two resistors or the one resistor. As far as the circuit is concerned, they operate the same way. So what does that mean? That means that there is the same current I flowing in both of these circuits, and that I would measure the same voltage across this black box in both circuits. It'd be V0. So what is that? So let's take a look here. First, let's start practicing Kirchhoff's laws. First one, or Kirchhoff's rules, whatever. So let's go with the loop rule. The loop rule says that the change in potential as I go around a closed loop, not delta V naught, is 0. So if I take this circuit and I make a closed loop, I'm going to go something like this. To write down the loop potential means that I have to say that delta V loop is equal to the change in potential for every element I cross. So that means the battery, that means R1, that means R2. I'm going to do the same thing over here. Now I would find for this circuit that delta V loop is equal to delta V battery plus delta V EQ. Now, the loop rule says that since this was a closed loop, I went from start to start. This is going to be equal to 0. The voltage of my battery is going to be V0. The voltage of my first resistor, because I'm going in the direction of current flow, I'm going to subtract IR1. I go through the second resistor, still in the direction of current flow. I subtract IR2. And so I get that V0 is equal to I times R1 plus R2. Alright. I can't do much else, don't have any other numbers, can't make any other cool cut substitutions. So let's head over here. Again, closed loop, so V loop equals 0. Delta V battery is V0. I think it has to be the same current because otherwise this whole thing doesn't work. The idea again is that I can replace these two boxes. So I have IR EQ this time. So this says that V0 is equal to I times REQ. Looking at these two equations, same V0, same I, which means these must be equal. R equivalent must be R1 plus R2. And you can see if I had an R3 and an R4, all of them in series, it would just be, I would keep adding them all up. So that is our first claim. Justified. Bam. Series circuit done. So let's take a look at parallel circuits. Well, in a parallel circuit, I'm going to have, again, a battery. And I'm going to have a branch in this. Something like this. So I have R1, R2. Wow, that was a really rough looking circuit. Let's see if I can do a little better this time. Like the resistors, keep them. Have I mentioned I love my computer? I love my computer. Anyway, and the claim again is that I can replace this by an equivalent circuit where I take out, still the same battery, but instead of these two parallel resistors, I have this one equivalent resistor. And the idea is that, I can again imagine a black box that contains these two parallel resistors and a black box that contains this equivalent resistor. And as far as the circuit is concerned, these two are identical. A current I flows into the black box, current I flows out of the black box, and everything behaves the same way. Now the trick here, and this is getting into Kirchhoff's other rule, is the node rule. By the way, if you need to hear more about these, you can hear me give like the 2-second version of them again in the other screencast. The node rule says that the current going into a node is equal to the current going out of a node. So why do we mention this? It's because there's a node right here. Not node in the pitch perfect sense. We're not talking nodes. Different node. Anyway. So I'm going to say there's some I1 going through resistor R1. Some current I2 going through resistor R2. And the node rule would say that I is equal to I1 plus I2. Alright. So let's take a look here. Because they're in parallel, I know from the loop rule, I can go like this. I can take a loop that goes through the outside. And this loop rule would say that delta V for my loop is the battery plus the resistor, and that's all that I go through in that loop. So 0 is equal to V0 minus I1 R1, because this is the current in R1, which means that I1 is equal to V0 over R1. I can do the same thing for R2. Start here, go around, take the lower root. So I2 is equal to V0 over R2, which means that I is equal to V0 over R1 plus V0 over R2. Alright, it's not too bad. Let's consider our other circuit. So if I look at this, I'm going to again do my loop rule. My loop is very boring. I just have delta V loop is equal to delta V battery plus delta V equivalent. And so closed loop, so the loop potential is 0. V battery is still my V0, even though I didn't write it down this time. Let me go fix that. It's totally been there forever. That's a different color. These things challenge me a little. And so now the one trick here is that, excuse me, because there's no node, there's no I1 or I2 in this, it's just I. So this time it's I are equivalent, which means that this says that V0 is equal to I R equivalent, and I is equal to V0 over R equivalent. So here I'm saying I is equal to V0 over R equivalent. Here I is equal to V0 over R1 plus V0 over R2. Taking these together, I can say that V0 over R equivalent equals V naught over R1 plus V naught over R2. Every term has a V naught, so I can cancel it, and I get, shockingly enough, our equation for parallel resistors. And again, we can see if I had more of them in parallel, I would keep, like this term here, I would keep adding in I3s and I4s, which would keep showing up here. And so I would add additional terms. So, hopefully this gives you some idea not only of where these equations come from, but how we can use the loop rule and the node rule to analyze circuits. So in your homework, we asked the question, what is the current in the battery? Well, if we, this is number 5 on your homework, by the way. If we look, the current in the battery is the current going into the equivalent resistor. So if we want to find the current in the circuit, which we usually think of as the current in the battery, then all we need to do is make the equivalent circuit. Let me write that down. Make equivalent circuit. And then use Ohm's law. Which is kind of like a side effect of the loop rule a little bit for a simple case. Anyway, hopefully this helps you kind of see where stuff is coming from and get a sense of how to use some of these tools as we, work to analyze circuits. If you have questions, as always, feel free to shoot me an email, put a post on Haiku, tweet at Ellis Physics, and otherwise just have a good one. See you later.